In Chapter 11 now we start to look at series and sequences. So Section 11, well, we're going to start with sequences. And we'll start with the definition. So sequence is a list of numbers written in definite order. So we start with, for example, there's two ways we could write this. The first one is we're just going to call it a sub 1, and that's our first term. We have a sub 2, which is our second term, a sub 3, which is our third term. Then we could kind of skip to the very end. We call it a sub n, which is our nth term. And some other ways to write this, we could have a sub n plus 1, which is our n plus, we call this n plus first term. Now we denote a sequence in these, what we call set brackets. I was calling them the squiggly brackets, but they're called set brackets. And we just list them this way: a sub 1, a sub 2, and on. Or we can just say it's the set of a sub n. Or we could say it's the set of a sub n as n goes from 1 to infinity. Or we might see it as parentheses of a sub n with a little n on the outside. All of this notation means the same thing, means we're working and looking at a sequence. So let's take a look at an example. Here we're going to use this notation. So we're looking at this expression of 1 over n sub n here. And all this means is n is an integer. So we start with 1. So 1 over 1 is just 1. Meaning this is our first term. So that's where we get the n's from. N is our first term. So when n is 1, we get a 1. When n is 2, we get a 1/2. When n is 3, we get a 1/3. When n is 4, we get a 1/4, a 1/5, 1/6, and so on. Or we might see something that looks like this. We could have 2 over the quantity 2 plus n as n goes from 3 to infinity. So if it's not telling us what n is starting at, then we just start with 1. So this would become, if n is 3, we're going to get 2 over 5, so 2/5. When n is 4, we're going to get 2/6. When n is 5, we'll get 2/7. When n is 6, we'll get 2/8, and so on. Now in this next example, whenever we see this -1 to the nth power, this means we're going to have alternating signs, because -1 to an even power is going to be positive, -1 to an odd power is going to stay negative. We just have to be careful with our calculations here. So here's another example. N is going to start with 1. So first we're going to have -1 to the first, which is -1. Then we'll have 1 plus 2, which is 3 over 1. So we're going to get a -3. When n is 2, we're going to get a +1 here times 4. Then we'll get 4 over 2. So that's just 2. When n is 3, we'll get a -1 here times 5. So we'll have a -5 over 3. When n is 4, we'll get a +1 times 6 over 4. So we'll get +6/4, and then so on. Some other things we're asked to find is if we're given a sequence, we want to find a formula for the general term. So let's take a look at an example there. So we call the general term a sub n of sequence of 1/2, -3/4, 5/6, -7/8, and so on. So a couple ways we could start. We could look at this as our first term, our second term, our third term, our fourth term, or we could call this as our initial term, and then this would be the next term after that. So it all depends on how you want to refer to it. These are the two ways. So let's start with just saying a naught, our very initial term here is 1/2. That means a sub 1 is going to be the -3/4. A sub 2 is going to be the 5/6. And then a sub 3 is going to be -7/8. So because we're alternating here, we'll say a sub n. We're going to need that -1 to the nth power because that's what's going to make our signs switch back and forth or alternate here. And then if we take a look at the numerator, they're all odd. So I'm going to say that this is 2n. That would make any even number. And then if I add 1, that's guaranteed to make it odd. So let's say here if n is 0, then we're going to get anything to the 0 power is 1. And then we'll get 1 times 1, so there's 1. And then my denominators are all even, so we could try this here as a 2n, but here if n is 0, then we would have a 0 in our denominator, so I have to figure something else out. So if n is 0, I still need to end up with a 2, so let's try a +2. And then let's see if this works. So I'm using these values as my n's. So let's see, when n is 1, I'm going to get a negative when I substitute -1 to the first. And then we're going to get a 2 times 1 plus 1, so there's my -3 up top. And then 2 times 1 plus 2 is 4. So you just want to check that it works for each value of n that we're using here. And again, just 2n in the denominator won't work when n is 0 here. All right, another example is that we can express sequences on the coordinate plane. So let's take a look at this sequence here as n goes from 1 to infinity on the coordinate plane. And it really comes down to just making a list of ordered pairs. So let's start when n is 1. Then we're going to get 1 minus 1 over 1, and then that's just 0. So first I have the ordered pair 1, 0. I'll just number out to 4 here. But on the y-axis, I'm just going to put a 1 right up here. So I'll kind of count by halves. So my first point is going to be here at 1, 0. When n is 2, I'm going to get 1 minus 1/2, which is 1/2. So I have 2 and 1/2. When n is 3, I'm going to get 1 minus 1/3. So that's going to give us 2/3. So I have the point 3 2/3. I'll say that's right about here. When n is 4, we're going to get 1 minus 1/4, so that'll give us 3/4. So we're plotting the point 4 3/4. So we're right about here. But as n keeps increasing, my expression is getting closer and closer to what? To 1. So here, a very important statement to make is that we do not connect the dots. We are not looking at any values in between, just these. So as we keep moving over further and further as n increases, our values are going to gradually get closer and closer to like this horizontal asymptote right here. So the values are getting closer and closer to 1. It's just another observation to make. And this leads to limits. We seem to bring back limits into everything that we're looking at here. All right, so let's take a look at another definition. So we say a sequence A sub n has a limit L that we write as the limit as n approaches infinity of A sub n is equal to L, or A sub n goes to L as n goes to infinity, if we can write the terms A sub n as close to L as we like, by taking n sufficiently large, by choosing a very large value for n. So there's a theorem as well. We say if the limit of f of x as n approaches, or x rather, approaches infinity, this is equal to L, and f of n is just going to be whatever term we're looking at for our sequence here. For all positive integers n, then this means the limit of A sub n as n approaches infinity is also equal to L. So it equates to the limit of our function. The only difference, though, is if we were to go to plot these points, we would not connect them. All right, so an example here. Since the limit as x approaches infinity of 1 minus 1 over x, so that's just the graph we were looking at, but I called it 1 minus 1 over n, is equal to 1. So as the x values keep increasing, our output values get closer and closer to 1, then we know the sequence of 1 minus 1 over n also approaches 1 as n increases without bound. So these two statements agree at all integers, because these values are still headed to the same place whether we're dots or we're continuous, so whether the dots are connected or not. We come to another definition. The limit of A sub n as n approaches infinity is equal to infinity or keeps increasing without bound. So this statement here means for every positive integer m that's greater than 0, there is an integer n such that A sub n is greater than m for all of the integers that will be greater than capital N here. So all this is saying is m is representing a positive integer, and if we choose a value greater than this integer, then all of the sequences in our, or the terms in our sequence will stay bigger than m. So in this case, we say that a sub n is divergent to infinity. Now, just as there were limit laws back in Calculus 1, there's limit laws for sequences. So let's take a look at those. We're going to refer to two sequences here. First, we have a sub n and then b sub n. And the notation here is saying that they're both sequences. But let's also say they're convergent sequences. So if a sub n and b sub n are convergent sequences, and c is a constant, then the following laws or properties hold true. So first, we say the limit of a sub n plus or minus b sub n as n goes to infinity. So saying the limit of the sum or difference is the same as the sum or difference of their limits. So we can separate them. The limit of a sub n as n approaches infinity plus or minus the limit of b sub n as n approaches infinity is convergent. Second one, we take the limit of a constant times one of the sequences here as n approaches infinity, then this is equal to c times the limit as n approaches infinity of a sub n. The limit of their product is also the same as the product of their limits. So if we have a sub n times b sub n, this is equal to the limit of a sub n as n approaches infinity times the limit of b sub n as n approaches infinity. Next, we have the limit of their quotient is the same as the quotient of their limits, provided our denominator is not equal to 0. So the limit of a sub n over b sub n as n approaches infinity is equal to the limit of a sub n as n approaches infinity over the limit of b sub n as n approaches infinity if the limit of b sub n as n approaches infinity does not equal 0. In our fifth one, the limit of a power is the same as of a term of the sequence or of a sequence here is the same as the entire limit of the sequence raised to that power. So we'll say a sub n raised to the power p. So this is the same as the entire limit of a sub n as n approaches infinity to that power. Now there's also an extra little theorem here called the squeeze theorem. And this says if we have a sequence that fits between two others, so if b sub n is in between a sub n and c sub n, for all integers greater than or equal to some given integer here, and the limit of a sub n as n approaches infinity is equal to the limit of c sub n, and that equals L. And if b sub n is in between that, then it has to meet that same limit as well. Then the limit of b sub n as n approaches infinity is equal to L. So it says b sub n better go to L as well if it's in between and these two are equal. So as you're seeing, this first section is full of a lot of theorems and definitions to really help us understand what's taking place with these problems, these sequences. So another theorem, if the limit as n increases without bound of an absolute value of a sequence is equal to 0, then the limit of the sequence here, a sub n, or the term as n increases without bound, is also 0. So just to point out that this may have some negative terms, but they are headed to 0 too. So let's get back to some examples. See, what is the limit as n approaches infinity of -1 to the n over n? So let's write this out. All right, so when n is 1, we're going to get a -1. When n is 2, we're going to get a +1 in the numerator, so we'll get a +1/2. When n is 3, we'll get a -1/3. N is 4, we'll get a +1/4. N is 5, we'll get a -1/5, and then so on. So we're going to write this as the limit of the absolute value of a sub n, as n goes to infinity, is equal to the limit, based on this last theorem here, as n goes to infinity, of 1 over n. No need to have the absolute value bars around it because we could take it away then. Should equal 0. So if I took the absolute values of all these terms, if I plotted this on a coordinate plane, they're getting smaller and smaller. They're approaching 0. So that's what this should equal to. So then we would say the limit as n approaches infinity of -1 to the n over n is equal to 0. Because if we were to separate these, all of these negative values, they started off lower, but they're moving their way up to 0, so they're approaching 0 from below it. And then all of the positive values are approaching 0 from above. So that's why we could write it. This is really the absolute value part here. But based on the theorem, we can just say that without the absolute value part, that's also going to equal 0. Let's take a look at another example. Let's find the limit as n approaches infinity of 7n over n plus 1. So let's start with this expression, 7n over n plus 1. Now, if you think back, I think we did this at the very beginning of the semester. If not, we definitely did this in Calculus 1, as we took a look at limits at infinity here, that we could just divide everything up here by n. There's a little trick we did. So we have 7n over n, and then we get n over n plus 1 over n. So this gives us 7 over 1 plus 1 over n. And then we would say, as n approaches infinity, this fraction is just going to head to 0. So now we're just left with 7. So then the limit as n approaches infinity of 7n over n plus 1 is equal to 7. Another theorem. All right, the sequence r to the nth power is convergent if r is greater than -1 and less than or equal to 1, and divergent for all other values of r. So we could write this that the limit of r to the n as n approaches infinity is going to equal 0 if r is greater than -1 and less than, or just less than 1. Because what does this mean? This means that r would be a fraction. So if you can imagine, if we had r was 1/2 and we raised that to the nth power and n kept growing and growing, this fraction starts to head towards 0 because we're getting an even bigger denominator here, so it's going to tend to 0. Even on the other side, if it's a negative fraction, the same thing is going to happen. And then this limit is equal to 1 if r is equal to 1, because r to any power is 1. Otherwise, it diverges. I do want to talk about this lower part, though. Let's see if r is equal to a -1, then we would get -1 to the n, which gives us -1, then 1, then -1, then 1. So in this case, we're not converging to anything. So again, we're going back to these two, that if the limit of r to the n as n approaches infinity, if r is between -1 and 1, it would converge to 0. If not, it's going to equal 1. But if r is -1, it does not converge to anything. And as I mentioned with the 1/2, any fraction here is getting smaller as n is getting larger. Another definition. For this one, we're going to talk about increasing and decreasing for a sequence. So we say a sequence a sub n is called increasing if every previous term is smaller than the next one after it. So if a sub n is less than a sub n plus 1 for all n greater than or equal to 1. So for an example here, a sub 1 is less than a sub 2 is less than a sub 3, and so on. It just means the terms in the sequence are getting larger. A sequence is called decreasing if the opposite is true. If a sub n is greater than the next term after it for all n greater than or equal to 1. And we say a sequence that is either increasing or decreasing can also be called monotone. So we'll look at this example, the sequence of 1 over n, which again equaled 1, then 1/2, 1/3, 1/4, 1/5. We could clearly see the terms are decreasing, so we would say this is a decreasing sequence. And a few more definitions. We can also refer to a sequence as being bounded or unbounded. So a sequence A sub n is bounded above if there is a number m such that A sub n is less than or equal to m for all n values greater than or equal to 1. So going back to our example of 1 over n sub n, again, if we were to just take a look at what I have above here, and what could be helpful is if you plot these points, they are not getting larger than 1. 1 is the largest value, so we would say is bounded above by 1. A sequence is bounded below if there's a number we'll call lowercase m So again, a sequence is bounded below if there is a number called lowercase m such that A sub n is greater than or equal to m for all n greater than or equal to 1. Again, going back to our example, so if we look at all these values, we're kind of seeing they are decreasing, but what's the lowest value they're going to get? They're never going to become negative as n keeps increasing here, and they're never going to be 0, but they're going to approach 0. So we'll say it is bounded below by 0. I don't know why I keep wanting to put equal signs. So if it's helpful too, if you're not quite sure what this is, maybe start plotting the terms of the sequence to help you see that a little bit better. So if a sequence is bounded above and below, then we can call this a bounded sequence. And then just one more theorem to take a look at. We call this the monotone sequence theorem. So we would say every monotone bounded sequence is convergent. Monotone meaning it has to be increasing or decreasing, and it has to be bounded. So that makes sense, doesn't it? If it's bounded, it's not taking off and going towards infinity or negative infinity, so therefore it has to be convergent. So again, increasing and bounded means it's convergent. Decreasing and bounded means it's convergent. And then going back to our example of 1 over n, we just said this is bounded above by 1 and bounded below by 0. It is also monotone. Therefore, this sequence is convergent. And like I said, we can make a little graph. All right, so we had our first point at 1. Then we had 1/2. Then we had 1/3. Then we had 1/4 and 1/5. So it starts to look like this. But it's bounded above by 1, bounded below by 0. So it means it would be convergent. All right, so that was section 11.1. Let me know if you have any